My name is Dimitrios. I am a postdoc in Singapore, and this is a joint work with Eric Allender, Mahdi Cherakci, Harsa Tirumala, and Ilya Volkovic. And these are my co-authors. So 3 of them are around here. Yes, Eric is there, and Harsa, and Ilya gets somewhere around. So this was presented in FST. Thanks. Okay. So this work was presented in FST TCS 2021. So you can also see Harsa's talk if you want. The meat of the presentation is basically the results, like some small discussion about the results and then a small discussion about the techniques. I didn't say what the paper is about, but maybe you have guessed because of the previous very nice talks. Actually, there have been some amazing talks in this workshop. Like I enjoyed all of them, and I'm very happy to be here and among you. Just to get that out of the way. So 2 years ago, this paper came out by Liu and Paz, where they showed the equivalence between the existence of one-way functions and the average case hardness of this meta-complexity problem, which is time-bounded Kolmogorov complexity. So this was the starting point of this work. Like when we saw that, we started thinking, like, what can we do with this paper? Apparently, many people started thinking like us, like by looking at the amount of papers that came out after this paper. So, like, one question that we had, okay, so they saw an equivalence between average case hardness of a meta-complexity problem and the existence of one-way functions. Can we do something like that, but for some NP-complete problem, that it is like a meta-complexity NP-complete problem? Now, why is this interesting? Because, like, it is in general, okay, maybe it is interesting to look at NP-complete problems in the hope of, at some point in the future, to be able to relate worst-case hardness with the existence of one-way functions. So, okay, this is an incomplete list. There are some meta-complexity problems that are NP-complete. After Liu and Paz, there are even more. Like, for example, Liu and Paz have showed some other Kolmogorov complexity variant that it is NP-hard, and we did it too. But like back then, I think that this was, okay, maybe I'm missing something, but this is basically like some very notable results. So, okay, we thought, can we do this, for example, for partial MCSP? So this is how we started thinking about this. Now, why did we choose partial MCSP? Because it seemed to be convenient to fit the framework of Liu and Paz. But like, I will get to that. Okay, so basically what we end up doing after trials and errors was to prove that one-way functions are equivalent to the average case hardness of a variant of MKTP. And this is KT with capital T, okay. So now let me just present some definitions to make sure we are all on the same page, and then we will see why this is true. And why do I mean by conditional variant, okay. Okay, so there have been like many talks also today explaining what is a one-way function. So like you know what it is. It's just like something is to compute, hard to invert, okay. About MKTP, I guess you know that too. Hanlin gave a very nice talk on MKTP. I will get back to Hanlin's talk later. So, okay, MKTP is like based on KT complexity. KT complexity is a variant of Kolmogorov complexity. And in order to define Kolmogorov complexity, you need to say something about universal Turing machines. Basically, it's just like some notation. Like I have a universal Turing machine U with random access to program D that runs in time T and has input Z. And the output is Boolean here. Basically, no matter what the universal Turing machine does, I just look at one output bit. I don't care about the rest. Okay, so now we can define Kolmogorov complexity formally. Basically, it's like minimize the size of the program that can generate any bit. Nice. KT complexity, you already saw that. Now, in the measure, there is also a term about steps that you can generate any bit, okay? MKTP, a decision problem based on KT complexity, fine. And now this is something that was useful for us, like in this question that we had earlier, like try to find an NP-complete problem that can capture, or it seems that can capture one-way functions. So basically here you just have some helpful string y in order to generate the bits of the string x. And MCKTP, again, a decision problem based on this decision variant. So now let's get to results. Let's discuss a bit about results, and then let's discuss a bit about techniques. Am I going too fast? Yes?
Just have one question. For the conditional one, are you given, like, can y be as long as x and you have oracle access to it, or is it like small, like the size of the program?
So as you can see here, like it's like slightly superlinear this y in practice, the way that we used it.
So then you're allowed, or the program can oracle access it?
So, okay, that's a good question. Let me go back. Here you mean?
Yeah,
yes,
yeah, y.
yes.
Yeah.
There is, that's a good question. If you want to talk like more about it, let's do it afterwards, because the thing is that there is some subtle issue there. You have like oracle access to both, but when it comes to program, you can jump and then you can move around also. This is like a bit non-standard variant of access. Like, so you have like this extended oracle access tape. This is how we call it. This is like a technical reason. It is about Rahul's work. Like, because we used his paper for the NP completeness part, and this is like where this was relevant, to have like different notion of access there. But it is, let's assume for now that it is oracle access to both. Okay? Other question? I think I saw some other. Yes?
Could you flash the next slide again? The Latin. Okay, so that is the class that you're going to be working with?
Yeah, this is the problem that we're going to look at.
Okay, and the function little m, we think of that as fixed once and for all, or what's the...
Like in our results, this is something slightly superlinear. Like 1 plus epsilon, like n to the 1 plus epsilon, something like that. Let's assume that it is something slightly superlinear. But I will obfuscate it, like in the statement of the results. You're not going to see this again, I think. Okay, so let's start with NP completeness. So this problem is NP complete under randomized reductions. Now, like I already gave away how we did it, like we adapted Rahul's work on minimum oracle circuit size problem, but I will go back to that later. So I will just state some results. Okay, so these are the results that relate the existence of one-way functions to the average case hardness of this problem. There is a problem here. The problem is that this direction works well. Like if you have one-way functions, you can get some nice average case hardness, some noticeable hardness. Sorry, the other way. Like if you have some like noticeable hardness in MCKTP, then you can get one-way functions. But like in the other direction, we were not able to show very significant hardness. Like hardness in this direction is on an exponential fraction of instances. This is the main setback of this work, that it doesn't exactly characterize the existence of one-way functions. Okay. Now, later, like I can come back to this to discuss. Yes.
So the quantifier, I mean, so when you say they exist if and only if it's hard on average on some polynomial fraction or
Yeah.
on which polynomial fraction? It's, there exists. Or,
Yes.
yeah.
Right.
Wait, there was the question. I didn't.
Like about
There was
the
another yes or no.
polynomial here. Like yeah.
Can it be any polynomial, or is it n to the 10?
There
or
is-
it,
there is a
or can I
polynomial.
choose? So there exists a
There
polynomial
exists.
such that this
Yeah.
holds.
Right.
So there's like a n to the 10 or something, and it's
Something
fixed,
like
and
that.
now it's your most.
Yeah.
So you use the uniform distribution for both x and y?
Yes. So, like you will like your answers, your questions like will be answered because like you will see that this basically follows like LUN-pass template, but like with a different function. So if you have seen LUN-pass, it's like basically like the same like quantifiers and everything behind this. Okay, so now some notes about the results. Now, like one paper that I didn't know about, and it came up on Twitter, like by people discussing on Twitter, is this in Pagliaccio and Naur paper. Actually, I didn't know that this paper existed. Like it shows that you can get like one-way functions from the average case hardness of this NP-complete problem, that is subset sum. I didn't know about it. Rahul Santanam told me about this. Actually, Rahul was like in my committee, and like when I was defending my thesis, this is when he brought to my attention. Okay, so yeah, LUN-pass have okay, so there is some story here with LUN-pass. They have like many papers. After we uploaded, and Yanni is there, like Yanni can like correct me if I say anything wrong. So like after we uploaded the fixed version of our paper on ECC, because there was a bug, I will get to that too. Like a day, like 1 or 2 days afterwards, Yanni and Raphael uploaded a paper that it is stronger than ours. Like basically they have like a tight characterization of the existence of one-way functions based on the average case hardness of an NP-complete problem. The good thing is that their work was inspired by our work that had a bug, okay, and we retracted it. And basically this work that was retracted was about an interesting problem that like we didn't do much about it afterwards, was like this sparse partial MCSP. We proved that it is NP-complete. And there was like a bug there in this like effort to characterize one-way functions with this problem. And in turn, this was inspired by the original LUN-pass paper. Like, there is some confusion maybe here. So LUN-pass published this very, very nice seminal paper. We thought that we can prove something similar for sparse partial MCSP. It was not correct. We retracted it. We fixed the paper with MKTP, and then a day afterwards, like this stronger paper by LUN-pass appeared. And there are many LUN-pass papers, okay? So I cannot cover all of them. They are related work, though. They are. And I also want to mention a paper that I also like a lot, Ilango, Ren, and Santana, because like they showed something like that, but for MCSP. And this was something that was missing, like characterize the existence of one-way functions, but the average is hardness of MCSP. Nice. Okay, so this is another result that we have, but I will not talk much about it. Basically, it says that this MKTP problem is interesting because it can capture log space computable one-way functions.
Okay, can I go back one slide before?
Yes.
Also, they show one function exists even only if MCSP is hard on average. Oh, that's very strong.
Yeah, but there is like
this goes back to like a distribution.
Yeah.
So
there is like locally samplable distribution. Yeah, I obfuscated a bit.
Oh, okay.
Yeah. And basically, like this result that I will not talk much about, it follows from Ren and Santana. Okay, because so they show this is the paper that Hanley presented earlier. okay, about like the average case hardness of MKTP. And we used this in our result. So basically, what it means is that like in this paper, if you take this paper, you can replace it by MCKTP. Like you can replace MKTP by MCKTP, and MCKTP is also NP complete. Okay. Okay. Time for techniques. I think I have time to at least cover some. Let's talk about the first result, which is, as I said, like adapting Liu and Pass. This very nice paper. Okay, so like they show that the average case hardness of KT complexity implies the existence of one-way functions, like the first part of their paper, and we took their construction, we changed it like 15 different times until it worked, and it seems that this idea here works. Let me explain what this is. So this S is like a program size parameter. T is time-bound parameter. Why is this helpful string? P is a program. So, and the output is the sum of S and T. The sum of S and T, right? Like KT complexity is the sum of these two. And then basically what you do is that you take this universal Turing machine and you run it for inputs from 1 to n. And you take 1 bit. So this is 1 bit. This 1 bit. So these are n bits here. And you also output y. So in one slide, I will just show you why this thing works, but without the proof of correctness. Okay? So this is a one-way function candidate. What if you could invert it? So basically what we hope to do now is that if you can invert it, then you can have an average case algorithm for MCKTP, because this is the contrapositive. Okay? So we want to prove that the average case hardness implies the one-way functions. If you can invert them, you get like an average case algorithm. So basically, if you can invert it, you can solve the search variant of MCKTP. And this is enough for now. Okay, let's solve the search variant. That's fine. And how do you do it? So you have as input the two strings x and y. So basically, you run the inverter for every reasonable value of this KT parameter, like this KT complexity parameter. And like these reasonable values of theta I, they are not many, right? Because like if you know that like this string has length n, then there are like linearly in n many possible values of its KT complexity. So if you want to brute force it, it's not a big problem. Like the values are not that many. So basically you do this for every reasonable value of theta I. You get some output, you see? So this is x. It is supposed to be generated by this UTM. This is y. And theta I is the sum of S and T. So you invert it, you go there, you have like this tuple, and then basically you just check all of them and you output the best. And what does it mean to be the best? You check that the program Pj generates any bit of x given y in time Tj. And you just take the optimal such pair. What do I mean optimal? Minimum description. That has the minimum description, okay? That like the sum of the size of p plus t is minimal, is minimized. All good? It's clear? You can interrupt me, okay? Now, about the other direction. The other direction is very standard. Okay, so let's see what we want to prove. That the average case hardness of MCKTP implies one-way functions. So here we are going to do again the contrapositive. That like if you have one-way functions, then MCKTP is average case hard. So we will prove the contrapositive again. And we will assume that MCKTP is average case easy. And then we will refute the existence of one-way functions in order to prove this. So let's assume that it is easy under the uniform distribution, okay? Then by using this nice paper about the NP hardness of multi-output MCSP, basically the appendix of this paper, like there is a learning algorithm for fixed polynomial size circuits for any exponent, for any fixed exponent that works infinitely often. So let's see why this is true very quickly. So okay, if you have an average case algorithm for MKTP, and then you go to this paper, ILO, then you can see that you can get this notion that they have that easiness on average with advantage. So this is an appendix where they try to relate partial MCSP to learning P-poly. So what does that mean? If it is like easy on average with advantage, it means that there is a distinguisher that can distinguish yes and no instances of MKTP with some advantage. So you have, basically you can have like some random string with high complexity, and then you can have some other string generated by small circuit that has like small complexity, and there is an algorithm that can distinguish it. Now, you can use here a hybrid argument. Basically, you have a spectrum of distributions. You have like one distribution where the inputs are like generated by small circuits, and another distribution where the strings are random. And you can distinguish between these two. So what you can do is that you can interpolate many distributions in between, and then use YAO to get a predictor for this circuit C. And this gives a learning algorithm if you have this predictor. So also, I see now that Bruno and Igor and Rahul, they are here, all of them. So, like if you, I think that is what you're doing there. And basically, if you have a learner, then you can create a distinguisher for function families. Like the first time that I saw this idea is in the conspiracies paper. So basically what you do is that like if you have a learning algorithm, you can basically use an oracle in the setting of the distinguisher game in order to train and test the hypothesis. So you train the learning algorithm, it spits out the hypothesis, and then you test it, if it is good or not. You can do it because you have the oracle. Okay? So this learning algorithm will perform well for functions from this function family F, because they are polynomial time computable, and so they have polynomial size circuits. But for a random function, we do not expect this to happen, because like they don't have polynomial size circuits in general. So you have a distinguisher for this function family. Now, if you have a distinguisher for any function family, actually, what does that mean? It means that there are no pseudorandom functions. And if there are no pseudorandom functions, then by Hill and GGM, there are no one-way functions. Is that okay? So we prove the contrapositive. I don't have that much time. How much time do I have? I have 7 minutes. So now about the NP completeness. Yeah, so here we used Rahul's work on minimum oracle circuit size problem. So I think that the main message of this paper of Rahul was that like MCSP remains NP hard even if you have some conditioning on some information. So basically this is what we did. We just like adapted this paper here. So let me just like give you like in one slide the intuition. Basically the idea is that, okay, so in the set cover, you have a collection of sets. What you can do is that you can encode in an oracle. So for every set S, you can have an oracle OS that basically only looks at the positions that are indexed by the set S, the positions of the truth table that are indexed by the set S. And then you do it for every S, and then you concatenate them, all these oracles. So this gives you a lot of information about the truth table. Now, one observation is that for any truth table, if I want to compute it, I just have to use a set cover. Like if I have a set cover, it means that I can look at every position of the truth table. So for every position of the truth table, there is a set in the set cover that can look at it. So if I have, for example, a small set cover, a small oracle circuit can compute this truth table, because I have already encoded all this useful information in the oracle. That's it. So basically, this could be just like a collection of oracle gates that they feed into a big OR gate. That's it here. Now, maybe I'm going a bit fast now because time is running out. Okay, let's take it easy. Like in the, okay, so in order to get this approximation that we want, we also need a lower bound. This is like a probabilistic argument. Basically, Rahul says that, okay, you have an oracle, fine, but still a random truth table is not expected to have very small oracle circuit complexity. And basically, this very small, it is a quantity that depends on the size of the optimal set cover. And the size of the optimal set cover comes up also in this upper bound. So you have an upper bound and a lower bound on the oracle circuit complexity that are simple functions of the size of the optimal set cover. And basically, this gives you this approximation. So you have like a lower bound, a lower bound and an upper bound that are functions of the size of the optimal set cover, and in the middle, it's the oracle circuit complexity. So you can approximate it. And basically, what we did here is just that, like, we took this proof and we rewrote it. But now, instead of an oracle, like, we just have a finite string that encodes the truth table of the oracle. So this is how the NP completeness of our result works. Okay. Now, open problems. Actually, it's one open problem. I'm not sure what you will think about it, but I had it written, so I kept it. So maybe this is like a very difficult problem. I'm not sure. So we have seen like equivalencies between the existence of one-way functions and average case hardness of meta-complexity problems. That, like, what could we possibly say between the average case complexity of meta-complexity problems and public key crypto systems, for example? I don't know. And some acknowledgements, of course. Okay, so I want to thank Rahul because, like, basically, like, he was also in my committee, and like the feedback that he gave me about the literature work was very important for this paper as well. Hanlin and Mikito reported bugs in an earlier like version of this paper. We had a lot of discussions with Janje and Raphael, and then with Ninad, Jan, and Russell, we had other discussions about this work. And thank you very much. Thank you.
Thank you so much. Questions, comments, solutions to the open problem? Anybody? Anything in the chat?
So, Dimitri, the reason you, like in the other direction, while function only implies like an exponential, like average case hardness of a MKTP, is this exponential comes from the reason that, like, to make the learning algorithm like this, in some sense, this range of the function is like too small, so it's like too sparse. So you need like a real strong, like, average case algorithm to.
Here. So it's in this step. Like, when we wanted to show that this 2.1, this is where this comes out.
Yes.
Like, where we wanted to show that we have this average easiness with advantage. To get this advantage, like these two probabilities to be significantly different.
So it's like 1 minus 2 to the.
It's like 2 to the n over polylog n.
Okay. I see.
So basically, like, so we want this to be you know, like inverse polynomial and so on, but then, like, the calculations were not working out here. Now,
Okay.
one question that I thought previously when we had pizza is why didn't we use here the other direction of your paper as well? And I think that the reason we didn't do it is that because like originally we had in mind MCSP and the circuit complexity of this conditional entropy preserving PRG that you had was not very clear to us how small the circuit complexity is. I think that is why we were biased with not using the second part of your paper here. Maybe.
Yeah, thanks.
Yeah.
Very good work. Thanks.
Thank you.
Anybody? Thank you. Oh, yes, sorry, you
Can
go
I
ahead.
ask a question? So can you, I mean, you are studying MKTP here, and I think Hanlin and Rahul show that that's characterized parallel Oneway function.
Right, right.
So can you also adapt combine your stuff with their paper to get some stuff for Oneway function in NC0? I don't know.
Yes. So you mean this?
Yes. Oh.
Yes. Basically, if you take Ren and Santana, like it works with our problem too. That's fine.
Wrong.
But I didn't want to talk much about it because already Hanlin talked about it,
Oh, I see.
and we only added it like last moment to the paper, to be honest.
Oh, I see.
So it's not very
Exactly.
Okay. Well, thank you so much.